Welcome to Mathematics Made Easy channel. Here it is linear algebra. In this linear algebra we are discussing vector spaces. Our vector space definition. A vector space V is a non-empty set containing objects or vectors UV, on which are defined two operations. Here for these three vectors we are defined two operations called addition and multiplication by scalars that satisfies the following conditions. Let's have the conditions. U plus V belongs to V. This is nothing but a closure property with respective addition. Next, U plus V is equal to V plus U. It is nothing but commutative property. Next, U plus V of plus W is equal to U plus of V plus W. It is nothing but associative property holds. Next, vector V contains a unique non-zero vector 0 such that U plus 0 is equal to U for all U plus U belongs to V. Means here vector additive identity is 0. It is added to a vector u. So again we are getting u. Now vector v contains a unique vector minus u called inverse of u such that u plus of minus u is equal to 0. So here we are defining inverse. So with respective addition, here it is have the 5 properties, that is closure property, commutative, associative and additive identity and inverse property. Now let's have the third last property. A scalar multiplication is defined such that if u is any vector in V, C and D are any two scalars. Now a scalar is multiplied over du. So here we are going to get CD of u. Next, C plus D of u is equal to Cu plus du. Next, C into u plus V is equal to Cu plus dV. Next, D is the 1 into U is equal to U. Means here 1 is the multiplicative identity. So all these are the properties for vector spaces. Subspaces. A subspace of a vector space V is a subset H of V that has three properties. The zero vector of V is in H. Here we are saying H is a subset of V. In this H we are having the zero vector. Next, second one is H is closed under vector addition. H is closed under vector addition. That is, for each U and V in H, then the sum U plus V is in H. Then U plus V is in H. So sum of two vectors is in H, we are saying. Now third property is H is closed under multiplication by scalars. That is, for H, U in H and each scalar is multiplied with respective H. Then the vector C dot U is in H. Now these three above properties says that a subspace H of V is itself a vector space. Why? Because already these three properties are in the vector space. That is closure property. U plus V is nothing but closure property, and C into U. C into vector multiplied with respective vector. It is a property of a vector space, and there we are having the additive identity 0. So all these three are in the vector space. Under the vector space, operations is already defined in V. So by this we can say every subspace is a vector space. Conversely, every vector space is a subspace. Why? Because the above three properties already is there in vector space. So we can say vector space is a subspace. Example. The set consists only the zero vector. In a vector space, completely zero vector we can show. So V is a subspace of V. V is called the here V is a subspace of V. How we can say V is called the zero vector subspace? As the set contains 0, so we call it as a zero vector subspace, and it is written as like the singleton set 0. Next, let us go for the second example. Let P be the set of all polynomials with real coefficients with operations in P defined as per function. Then P is a subspace of the space of all real valued functions in definition R, defined on R. So here for each n greater than or equal to 0, Pn is a subspace of P. We are saying Pn is a subspace, means P0, P1, P2, P3, 4, all these are the subset of the P. Now this capital P is the set of all polynomials. P0 is nothing but a polynomial with respective 0. 0 in 0 plus 0 into x plus 0 into x square plus so on is equal to 0. It is a 0 polynomial. P1 is nothing but with respect a, just simply ax plus b is the P1. P2 means ax square plus bx plus c is taken as the P2. P3 is nothing but ax cube plus bx square plus cx plus d is equal to 0. That is P2 polynomial. Like this we are going to have. Now P3L polynomial. All these are the subset of P. All these are the subset of P. Now this P contains a 0 polynomial also. Now let us have the sum of two polynomials. Means we can add any two polynomials, we are going to get a polynomial. Step 3. If we take the a scalar multiple of a polynomial in Pn is also a Pn. How can we say? Means suppose example x square plus x plus 1 equal to 0 is a polynomial of degree 2. Now if it is multiplied by 2, so we are going to get 2x square plus 2x plus 2 equal to 0. So it satisfies the all the three properties. So we can say this is the subspace. P is a subspace of a R, we are saying. Next, let's have one matrix like this. Capital H is equal to a matrix as S, T, 0 we are saying, and S and T are the real values. Show that H is a subspace of R cube. Now here already in this set we are having 0, so the 0 vector is in H, we are saying. The property of a subspace is first property is satisfied. Next, if we add these two, that is if you take the H1 as S1 T1 0 and H2 as S2 T2 0 and add the H1 plus H2, we are going to get S1 plus S2 T1 plus T2 01 plus 02. So again we are going to get same the property same the set as H. So H is closed under vector addition. And vector multiplication means if you multiply here with respect to some constant, we are going to get that is C into H is equal to CS CT C0, means it is a vector multiplication. So here it is a subspace. Thanks for watching my channel. Please do subscribe and forward to your friends. Thank you.